Hey guys, and welcome back. Today we're going to be going over your Unit 2 study guide on plate tectonics. I wanted to go over this with you just to make sure that we were all on the same page for your Unit 2 test. So this is probably going to be split into two parts. There's 20 questions, so I'm going to go over the first 10 in this first video, and then we'll do the last 10 in the second video. But basically I'm just going to go through this with you and start filling it in, and then going over some of the answers. So here at lesson 1, layers of the earth, we need to highlight the correct answer. So here, number 1, remember we talked about the different layers of the earth. So we had our crust, our mantle, our outer and our inner core. That was our very first lesson for Unit 2. So it says continental or oceanic crust is thicker and consists mostly of granitic rock. So the answer here is going to be our continental crust. So I'm going to highlight this one. And I'm going to use blue. Okay, so continental crust is the answer here. So it is thicker and consists mostly of granitic rock. Number 2 says the outer core is solid or liquid, while the inner core is solid or liquid. So our outer core, remember, is a liquid. And how do we know this? So our outer core is a liquid because we know that the S waves are deflected around it. So remember when we talked about earthquakes and seismic waves, S waves can go through solids, but they cannot go through liquids, whereas P waves can go through both solids and liquids. So we know that the outer core is a liquid because when we measure those S waves, they're deflected around the outer core, indicating that they can't pass through the core, meaning that it is liquid. So the outer core is liquid and then the inner core is solid. Remember, there's just too much pressure on our inner core for it not to be solid. So the outer core is liquid and the inner core is solid. Okay, the mantle or the crust makes up 82% of Earth's volume. It has a solid layer and a molten layer. This is where convection currents happen. So convection currents are going to occur in our mantle. So I'm going to highlight our mantle. So remember, our convection currents are what drives plate tectonics. So, I made this to be black and I want the highlight to be blue. So remember that in our mantle we have those convection currents. So we've got the rocky upper layer of the mantle and then we have that molten inside. And the things that are actually driving the plates, so driving the plates that are moving on top of the lithosphere or on top of the asthenosphere is the movement of those convection currents. So again, the rock is heated as it's close to the core. So where that heat source is, that rock gets really hot, it expands, it becomes less dense, and it rises up. And then as it gets closer to the crust, it will cool down and then become more dense and sink back down. And that cycle goes over and over. It's very important that we understand that the convection currents in the mantle are what drives plate tectonics. Okay. So now let's move on to lesson 2, which was continental drift. Here we talked about Alfred Wegener and his theory of those moving continents. And there was that video that you were supposed to watch of the Alfred Wegener song that was very catchy and could get stuck in your head a little bit. So he had 4 main pieces of evidence that kind of showed us that continental drift was, an actual concept. So what were those 4 things? Well, number 1 was puzzle pieces. When you look at the different edges of the continents on a globe, you see that they could fit together like a big puzzle. So this was his indication that the continents were once together in one large continent, and over time they had moved away from each other. So they broke apart and they moved away. His second piece of evidence that we're going to talk about are ancient climates. So remember, there was evidence that there were ice sheets in Africa. So when we think about where Africa's position is in the world right now, it's close to the equator, okay? And the equator gets most of the sun's radiation from the earth. And because it absorbs so much of that radiation, it heats up a lot. So Africa is typically pretty hot. But there's evidence that a long time ago it was covered in snow and ice. That would not be possible with Africa being in the position it is now. So this would be our evidence that at some point Africa was closer to the poles, where it would be really cold and you could actually have large sheets of ice. And then over time, as the plates moved, Africa moved along with it and settled into its place where it is at the equator now. Now, Africa won't always be at the equator, because as time goes on and we get more of these millions and millions of years on Earth, the plates will continue to move with plate tectonics. So we have puzzle pieces, we have ancient climates, and we also have rock types. So we'll talk about the formation of rocks later on in this course, but basically different rocks are formed under very specific conditions. And what he found was that, especially along edges of these continents, they have very specific same rock types. So this is the indication that these rocks were formed at the same time and then broke apart and moved away from each other. So we have puzzle pieces, ancient climates, rock types, and then we also have fossils. So our last piece of evidence are those fossils. Now, he found fossils of the same organisms across different continents, which on the evolutionary scale doesn't really make much sense, okay? You guys haven't had biology yet, but when you get there, you'll learn how organisms evolve, and typically they evolve in response to their environment, so where they are. So the likelihood that the same species would evolve in the same exact way and leave the same exact fossils behind across an entire ocean is very slim, okay? And it's even less likely that the species could evolve on one continent and then swim across an entire ocean to get to the other one, right? That makes sense. So basically what these fossils indicate is that all these organisms lived in one area at the same time. They died, were fossilized, and then as the continents broke apart and moved away from each other, the fossils made their way onto two different coasts of two different continents as they broke up. So the name of the supercontinent that existed long ago was Pandora or Pangaea. And the answer here is Pangaea. So Pangaea is the supercontinent that existed. So Pangaea was the first supercontinent that eventually broke up into Laurasia and Gondwanaland. That's hard to say. And then eventually broke up into the continents we have today. Number 6 says, many scientists did not believe Wagner's theory because he could not explain why the plates were moving. We now know that the continents are moving because of blank in the mantle. The answer here are convection currents. Okay, remember, this is one of the most important concepts from continental drift and also plate tectonics. The movement of the plate is caused by the convection currents in the mantle. And again, that's where that magma in the mantle gets heated. It rises. As it gets to the top of the crust, it will cool down, become more dense, and then move in that circular motion. So as it falls, the process starts again, and it just keeps going in circles, which will push the plates apart. Now, 7, 8, and 9 refer to our plate boundaries. So we're going to fill in this table below for our plate boundaries. So we're going to do the direction of movement, the geographic formations, and the examples. Okay, so divergent boundaries move away from each other, and typically what we get here are going to be ridges, right? This is where we have two oceanic plates typically moving away from each other, and as they move, you get that magma that pushes up and comes out in the middle and starts to spread and make new crust. So an example of this would be the Mid-Atlantic Ridge. Okay, so we do get ridges and also rift valleys. And a lot of times these are on the ocean floor. With a transform boundary, we get movement side to side. So plates will slide past each other. And again, all these pictures as well are in your notes from lesson number 3. Geographic formations or geographic consequences, here we get earthquakes. Okay, so remember, the movement of these plates sliding past each other will cause the earthquakes. And then finally, we have our convergent boundary. So our convergent boundaries have different things. So we've got continental-continental, continental-oceanic, and oceanic-oceanic. So the first one we're going to talk about is the continental-continental. So this is where two continental plates are coming together. And no matter what, actually I'm going to delete that, because no matter what the direction of movement, you have two plates colliding. Okay, so when we have a convergent boundary, no matter what type of plates are moving into one another, they are colliding. So you've got two plates moving towards each other and colliding. In a continental-continental collision, you would just have non-volcanic mountain ranges. So that's where two continental plates meet. At a continental-oceanic, you would have volcanoes and trenches. So this is going to be where a continental plate meets an oceanic plate. The oceanic plate will always be subducted beneath the continental plate because it's denser and heavier. So this oceanic plate will be subducted, and then you get volcanoes on the land and then trenches in the ocean. And then on an oceanic convergent boundary, you will also get trenches in the ocean, and then you'll get volcanic island arcs. So with volcanic island arcs, again, the lava and the underwater volcanoes are erupting, and then over time, as that magma flows from underneath the mantle, you will get the formation of new crust and eventually get island arcs that are kind of in the middle of the ocean. So examples of this, so for our mountain ranges, we have the Appalachian Mountains, right? Appalachia. Didn't spell that right the first time, which is kind of terrible because I went to App State. And then also volcanoes and trenches. So an example of a volcano would be like Mount St. Helens is a volcano. And then the Marianas Trench would be an example of a trench. Okay, so those are our boundaries we have to know. We have to know the difference between divergent, transform, and convergent. And then we also need to know the difference between these convergent boundaries as well. Remember, oceanic crust is always subducted underneath continental crust. And then at oceanic boundaries, one of the plates will be subducted beneath the other to give us those volcanoes. So we're going to jump on to lesson 4. We're going to wrap up this video with question 10, and then I'll make a new one for the next 10 questions. So lesson 4 was the deformation of the Earth's crust, which was also faults. So we do need to know the different types of faults. But the bending, tilting, and breaking of the Earth's crust is known as plate movement, compression, or deformation. Well, since we're talking about deformation of the Earth, we know that the bending, tilting, and breaking is just known as deformation. Plate movement is the movement of the plates, and then compression would be like a squeezing motion, which doesn't really apply here. Okay, so I'm going to cut this video here and make a second one going over the second half of your study guide. If you guys have any questions, let me know.